Hello students, my name is Shashank Shekhar. So let us continue with the exercise of solution. So question number 14 says that what is positive and negative deviation from Rod's law, and how is the sign of delta H mix related to positive and negative deviation from Rod's law. So we know that according to Rod's law that the partial pressure of a gas of each volatile component in a solution is directly proportional to its mole fraction. Now sometimes the solution which does not follow Rod's law observed. The solution which obeys Rod's law over the entire range of solution are called as ideal solution, and the solution which does not obey are termed as non-ideal solution. Now the two cases can arise. Then the partial pressure that was being say predicted by the Rod's law is less or more than the actual pressure. So for two cases we call it as positive and negative deviation. If the pressure is more than the expected, okay, so if the partial pressure is more than the expected, then we call it as positive deviation. If the partial pressure is less than the expected, then we call it as negative deviation. Now if I talk about the graph, so this is for positive deviation and this is for negative deviation. So here you can see that this is the ideal case. Okay, so this is the ideal case, and due to positive deviation the partial pressure is greater than the actual or the ideal pressure, right? Here also you can see. Now this is called as positive deviation. Okay, this is called as positive deviation. In this case we can see that there is a negative deviation, that the pressure that is being observed is smaller than the actual than the predicted pressure according to Rod's law. Next is vapor pressure of two component solution. So for next question with further solution. So it says that vapor pressure of a two component solution shows negative deviation from Rod's law. In case of an ideal solution, the enthalpy of mixing of pure subcomponent for forming the solution is 0. So we know that for a pure solution it is the del H is greater than 0. Now in case of solution showing positive deviation, the absorption of heat takes place. What will happen? The absorption of heat will take place, which will result in delta H positive. So it is the case which is called as positive deviation. In this case, what happens? See, what is the reason for first of all this positive and negative deviation? So when we mix two things, say A and B, then two cases can arise. Okay. Now suppose A and B will mix, then there will be an interaction between AB. Now if this interaction is less than the AA or BB interaction, then in that case we can see a positive deviation. Now what is the basis of this? See, if now AB are not interacting in the same way as AA was interacting with A and B was interacting with B, then that would result in kind of less interaction and less force on A and B. Alright, now they will have a much more chance of escape from the solution. That would result in an extra partial pressure, that is results in a positive deviation. Now if you want to mix such two compounds which do not want to say mix, then you have to supply heat in that. Therefore delta H will be positive. Now if I talk about the negative deviation, it occurs because the AA or BB interaction is greater than the AB interaction. So this will be the case of negative deviation. This will be the case of negative deviation, means the AB interaction is greater. Now since attraction is greater, that means more stability. More stability means release in heat. So release in heat means delta H negative. An aqueous solution of 2% volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molar mass of the solute? It is asked. So the question says that we have an aqueous solution of 2% non-volatile solute, in which 2% is non-volatile solute. and it exerts a pressure of 1.004 bar at the normal boiling point of the solvent. So we have to calculate the molar mass of the solute. So vapor pressure of the solution at normal pressure is given as 1.004 bar. Now what would be the vapor pressure of pure water at normal boiling point? It would be 1.013 bar. Okay. Now mass of water is 98 gram and mass of molar mass of solvent is 18 gram. Therefore, relative lowering of vapor pressure will be equals to P01 minus P1 by P01. That will be equals to the number of moles of 2 or divided by number of moles of 1. That is given mass of 2 by molar mass of 2 divided by given mass of 1 by molar mass of 1. Okay. So what is being said in this question is that for a thing to boil, the vapor pressure of the solution should be equal to the atmospheric vapor pressure, right? Now it is being said that we take a condition which is a kind of lowering of vapor pressure. So it is seen that at the boiling point of the solvent, the vapor pressure is lower by how much? It is 1.004. Okay, so this is the vapor pressure that is being seen for the solution at the boiling point of the solvent. Since this vapor pressure should be equal to 1.013, but it is not so because of the addition of the solute. So we can try to find the relative lowering of vapor pressure through this. So what is the lowering? It is 1.013 minus this much divided by the actual pressure 3. Now we got this, we put the value of the remaining one. So we have 2%. We are considering that we have 100 grams of this. Okay, so out of which 2% is this much. Okay, so that would give us the mass of M2, right? It is a very good question. Okay, I think it is a very good question because a very clear idea of many things is to be made here. So first of all, you must know that at boiling point, the vapor pressure of the solution or the vapor pressure of the thing which is to be boiled must be equal to the vapor pressure of the atmosphere or the pressure of atmospheric pressure, right? And atmospheric pressure is this much. If it is not so, then how much about how much amount is lowered, we have to calculate, and then we have to calculate the relative lowering. Okay, clear? Next question. Heptane and octane forms an ideal solution at 373 Kelvin. The vapor pressure of the two liquid components are this and this respectively. What will be the vapor pressure of the mixture of 26.0 gram of heptane and 35 gram of octane? How will calculate it? That is very simple to calculate. Okay, so first we'll calculate. We know that the vapor pressure of the pure octane and heptane is this and this. It is given. Now we'll calculate the molar mass of heptane. Therefore, the number of moles of heptane will be given mass by molar mass, and the molar mass of octane is this much. So the molar mass of octane, number of moles of octane is this plus. Therefore, the mole fraction of x1 will be this, and mole fraction of octane will be this. First, then we will calculate P1 is equals to x1 P1 naught, which is given here, and we will calculate P2 is equals to x2 P0 2, where P2 and P1 are the pressure that is not of the pure form, that is of the solution form, whereas P01 and P02 are for the solution form of the solvent form, that is the pure form. We'll calculate this, add those both P1 and P2 to get our final vapor pressure of the solution. The vapor pressure of water is 12.3 kilopascal at 300 Kelvin. Calculate the vapor pressure of 1 molar solution of a non-volatile solute in it. Okay, so it is being given that the vapor pressure is 12.3 kilopascal, that I am writing it as this much. Now let us suppose that the vapor pressure of the non-volatile means the solution is X. Therefore, the relative lowering will be this much. Further, what do we need? We need the moles of, say, your non-volatile solute. So it would be, so we have 1 molar solute, that is 1 mole is dissolved in 1 kg. So 1 by, what is non-volatile solute? We don't know the number of, see, the number of moles is given. We do not know the number of moles of the water, but we know we have 1 here. So to convert it to the number of moles, we multiply it by, divided by 18. Okay, that would give us this much. Further, we will calculate it for x to get the value of our vapor pressure of 1 molar solution of non-volatile liquid. So 1 molar solution means 1 mole of the solid is present in 1000 gram. Okay, so therefore the number of moles of solid will be 1000 by 18. So first they calculated number of moles, then we have used the mole fraction to calculate x2. Now it is given that water is this much. They will use, now we can use this relation to find the mole fraction formula. Okay, clear? Calculate the mass of a non-volatile solute. You have to calculate the mass of a non-volatile solute. And the molar mass is 40 gram per mole. Now it is dissolved in 114 gram of octane. So the mass of solvent is given as 114 gram. So that we can reduce the vapor pressure to 80. So P is given as 80. We have to calculate the mass of the non-volatile solute, so such that the vapor pressure is reduced to 80. So let the vapor pressure be P01 at the initial condition. Therefore, we can use this formula, that is P1 is equals to P0 x1, which will be the vapor pressure of the octane after dissolving. It is this one, right? So we know this. Therefore, we can calculate P01 here. Next, the molar mass is given, mass of octane is given, and molar mass of octane we can calculate using this formula to calculate the number of moles. Further, we can use this formula that we have, okay, to calculate this W2. So here they have used the Rod's law, P1 equal to x1 P1 naught. We know this. P1 is equals to x1 P1 naught. So they have used this thing. So we know here that the pressure is given as how much? Pressure is given as 80, right? Pressure is given as 80. Therefore, they have divided by 80 by 100 to get this thing. Next, a solution containing 30 gram of non-volatile solute in 90 gram of water has a vapor pressure of 2.8 kilopascal at 298 Kelvin. So we have a solution which has 30 gram of non-volatile solute. So mass of solute is 30 gram. Exactly 90 gram of water. Mass of solvent is 90 gram. And the solution has a vapor pressure of, so I am considering P1, which is the solution vapor pressure, or P, just simply P, as 2.8 kilopascal, or 2.8 into 10 to the power 3 Pascal. Further, what we have done, we have added 18 gram of water in, then added to the solution, and the new vapor pressure become 2.9 Kelvin. So next, they have taken a new situation in which The mass of solute is kept same. Only we have added some of the solvent. So now the mass of solute will be still the same, that is 30 gram, but the mass of solvent will be 18 plus 90, that would give us 108 grams of solvent. Now in this case, the pressure is written as 2.9 into 10 to the power 3 Pascal. Okay, so these are the two cases. I am considering them as P1 and P2. If we calculate the relative lowering of vapor pressure for both cases, what will be the, so it will be P01 minus P1 by P01 is equals to, so the molar mass of the solute we have to calculate. The molar mass of the solvent will be 90 by, we have 90 here. We do not know the molar mass of the solute. We know the mass of the solute, it is 30 to 18 first case, and that is equals to how much? That is equals to P01 minus 2.8 into 10 to the power 3 divided by P01. For the second case, P02 minus P2 by P02 is equals to 30 into 80 divided by 108 into M2. Now we will just put these values here. P02 minus, what is the value of P2? It is 2.9 into 10 to the power 3 by P02. Now we know that if we just put this value of P01, so we know that P1 is equals to P01 x1. Okay, so we know this formula. So if we put here, then P01 will be equals to how much? 2.8 into 10 to the power 3 that would give us, finally, if we want to calculate P01 from here, that would be P1 by x1. P1 is 2.8 into 10 to the power 3 divided by x1. X1 we don't know. Okay, x1 is just the nothing but the mole fraction. Okay, so let us keep it P1 here right for now. P01 for here. So here will be P01. Now the relative lowering will be this much, and for this it will be this much. Now this will be same, right? This is not will different. Why? Because the pure solvent is same. We are not differentiating the solvent. So what do we do here? Is we formulate P0 from both from here. Okay, we calculate P0 from here. So there are two equations and two variables. We can solve it very easily. So this and this will be cancelled. 3 6 9, 3 6 18. That is 6 by m2. 6 by m2. So let me write it on a different page. 6 by m2 is equals to P0 minus 2.8 into 10 to the power 3 divided by P0. Then we have 30 into how much? 30, 3 3 9, 3 6 18. That is 36. 18 2 36, 2 5 10. So 5 by m2. This is equals to P0 minus 2.9 into 3 P naught minus 2.9 into 10 to the power 3 by P naught. Now, if we just, what do? We can just equate both of this. We can equate both of this. We can write 1 by m2 from this equation. 1 by m2 is equals to P naught minus 2.8 into 10 to the power 3 divided by P naught. This is totally multiplied by 1 by 6. Here we can write P naught minus 2.9 into 10 to the power 3 divided by P naught, which is multiplied by 1 by 5. This is 1 by m2. This is also 1 by m2. Let us equate both of this. Right? This is equate both of this by P naught is equals to P naught minus 2.8 into 10 to the power 3 2.9 into 10 to the power 3 by P naught. This P naught and this P naught will get cancelled. We have 1 by 6 here. We have 1 by 5 here. Now we will cross multiply it. That would give us 5 P naught minus 2.8 into 10 to the power 3 into 5. And one will have 6 P naught minus 2.8 into 10 to the power 3 into 6. If we bring this here, that would give us P naught is equals to 2.8 into 10 to the power 3 into 6 minus 2.8 into 10 to the power 3 into 5. So 6 minus 5, 1. So P naught is equals to 2.8. Sorry, this is 2.8, this is 2.9. This is 2.9. This is also 2.9. Now let us multiply this. What we will get? We will get 6 8 48, 4 carry, 6 2 8, 6 2 12 for 16.8 into 10 to the power 3 minus 5 9 45, 4 carry, 6 2 12 for 16 into 10 to the power 3. That would finally give us 16.3 into 10 to the power 3 or 1.63 into 10 to the power 4. So this would be your pressure. Now what would be the molar mass? You can plug this value here for molar mass. So that would give you 1 by m2 is equals to P naught minus, so our P naught is 1.63 into 10 to the power 4, 1.63 into 10 to the power 4 minus 2.8 into 10 to the power 3 divided by 1.63 into 10 to the power 4 multiplied by 1 by 6. Just calculate this, cross multiply this to get a molar value. So they have done the same thing. They have calculated number of moles. Okay. Further, we have used this formula for the first case to get this equation. We can use the same formula for a different situation. Equate both of this to get two different values of our. So it is 2.9 kilopascal. It is 6 kilopascal. Now they have calculated the molarity out of this. Second question. So we can use this thing to calculate the P naught one also, which comes out to be 3.53. Next question says a 5% solution of cane sugar in water is freezing at 271 Kelvin. Okay, so freezing point is given. This is TB of solution. And we already know the boiling point of water is 373 Kelvin. Okay. So we have to calculate the value of Kb from here. So that would be 370. That would be T naught B minus TB. T naught B minus TB is equals to Kf m. That is the molality. So therefore 373 minus how much? 271 is equals to Kf. You have to calculate. It is given that 5% mass by mass solution is this. So in 5 kg or 5 gram is dissolved in 100 gram of water. If you divide this 100 gram by 18, then that would give you the, if you divide, so if we keep it in kg further, right? So this would be 100 kg. This would be 10 to the power minus 3 grams. So I am converting it into gram. Okay. And what is the thing that is being dissolved? That is cane sugar. So the formula of cane sugar is C12H22O11. That would give you 1 Cl12 means C12 means 12 12 is 144. It's 22, and 11 into 16 gives us 16 plus 16, 16 plus 16, 167. This would result in 7 to 9 for 13 1 carry, 6 for 10 13 1 carry, and 333. Okay. So is it true? It is 176, not 167. So 6 for 10, 12 1 carry, 7 for 11, 11 and 3, 14 1 carry, and 342 gram per mole. So this will divide by 342. Once you calculate Kf from here, then you can put this Kf value here in 5% glucose, and then you can calculate your boiling point. Let us see the solution. So first they have calculated del Kt as I have told. Then they have calculated the molar mass. After that, what is the mass of the water? Further, the number of moles of cane sugar will be 5 by 342. Therefore, the molality will be this much. Then we plug this value in this formula to get the value of Kf. When it is found, then we can use this Kf value to calculate it for the 5% glucose. That is 0.2. So this was for today's class. Thank you.